Okay, so today we're going to continue our discussion of thermochem, which is still a part of Unit 3, Area of Study 1 of VCE Chem. And so we're going to be expanding on the foundations we laid in the last video and discussing two study design dot points. The first one regards thermochemical equations. So we're going to have a discussion on what they are, what their use is in terms of VCE Chem, and also what differentiates them from a regular run-of-your-mill equation. So we're going to be talking about that. We're also going to be discussing combustion reactions. We're going to be focusing on the two differences, which is incomplete and complete combustion reactions. And we're going to be discussing the nuances with that. And our final discussion in the second dot point is going to be using specific heat capacity of water, so Q equals mc delta T, to determine the enthalpy change or the delta H value of a fuel. Okay, so we're going to start off our discussion by touching on thermochemical equations. Now, these are pretty straightforward, if I do say so myself, and they're really similar to the normal equations you would have encountered all the way in other parts of high school as well. So I think the best way to describe this is just to use an example. So we're just going to go with this equation here, so which is nitrogen gas plus oxygen gas, and that produces another gas, which is nitrous oxide. Right, so on the surface here, it's a pretty straightforward reaction. You've got two gases to creating two molecules of another gas, which is just a combination of the two other gases. Pretty straightforward equation, no dramas here. But if you're a chemist or you're someone who's trying to actually create this reaction and do it in real life, you might want to know some more things about this. So if we go back to the video we discussed last time, talking about exo and endothermic reactions, you might want to know, is this an exothermic, is this an endothermic reaction? Is this reaction going to release a lot of energy? Do I need a lot of energy to actually allow this reaction to occur? And these are all things that thermochemical equations tell you. So the first difference, and the only real difference, is you have a secondary aspect here, which is the energy release. Okay, this is the delta H value, and that tells you how much energy is released or absorbed by this reaction. So for this specific reaction, it is an endothermic reaction that absorbs 180 kilojoules. Right, so that tells us a few things. Obviously, it's got a positive sign, so we know that it's going to be an endothermic reaction. It's going to absorb energy from the surroundings. If this was an exothermic reaction, this would be a negative, and then we could understand that it's going to release energy. Another thing that's important about these thermochemical reactions is the coefficients in front of all these reactants. So here we have like an implicit 1 present. So one nitrogen gas molecule and one oxygen gas molecule, they both react in a 1-to-1 ratio to produce two nitrous oxide molecules. Now, when we go a bit more into mole ratios, this concept is going to be solidified, but this 1-to-1 aspect means that this kilojoule value is per mole, right? And usually you'll find them per mole. If this was, for example, doubled, so if it was 2N2 plus 2O2 gives rise to 4NO, so I've just doubled everything, then this delta H value would then be, again, double this value. So it would be plus 360 kilojoules per mole, right? So that's an important aspect that is good to grasp, because sometimes you can get given an amount of energy that's released, and you have to work around with these ratios to find out how much of the original reactants are used, how much of the products are formed, etc., etc. Okay, so now we're going to begin discussing combustion reactions, which is going to be by far the most common thermochemical equation or reaction that you're going to encounter. And within combustion reactions, there are two main subtypes. There's complete and incomplete. So we're going to discuss complete first because, again, it's more common and the one you're going to encounter the most. So the generic sort of formula for a complete combustion reaction is a fuel reacting with O2, which is a gas, to produce carbon dioxide gas and water. Now, an important thing that distinguishes complete combustion from incomplete combustion is that this oxygen gas is in excess, which means that this fuel can burn completely and oxygen is not the limiting reactant. So an example of something like that just basically would be like CH4 plus O2 gives you CO2 plus H2O. Then you would obviously balance it, so you have 4 hydrogen on this side, 2 here to get 4 on this side, 2 here to balance the oxygen. And so that would be your combustion reaction for methane gas. And then you could make it a thermochemical reaction by chucking in the enthalpy value, which in this case would be negative 890 kilojoules per mole. So that's just one example of a complete combustion reaction. There's many different types. And a lot of these values for your enthalpy are given in your VCE data book. So you don't need to memorize these values or anything like that. Moving on now to incomplete combustion. The main thing that separates this from complete combustion is the fact that the oxygen gas will be the limiting reactant. So there are various different types of incomplete combustion reactions, but the most common one is something like this, which you have the same reactants, but you produce carbon monoxide instead, and you still have the water. Now, you may also produce carbon, so that would be in the form of soot or some sort of particulate matter, but the reaction will usually tell you what form the incomplete products will take, but most of the time it will be carbon monoxide and water. And again, it's important to note that the oxygen gas in this case is limited, and thus the fuel cannot be fully oxidized or fully reacted properly to form the preferred products of carbon dioxide and water that we see in complete combustion. Okay, so we're on to our last topic, which is going to be the concept of using specific heat capacity, or Q equals mc delta T. That is the equation, to find the change in enthalpy, or the heat energy value of a fuel. So the kind of concept that this relies on is kind of goes all the way back to the first video where we were discussing the conservation of energy. The idea is that if we have some sort of apparatus here, so let's say there's a beaker of water here, it's filled up, and we know how much water is in here, how many grams of water. And we have some sort of spirit burner or some sort of apparatus here that burns a little fuel. We can figure out that obviously if this water is heated to a certain level from its original starting point, then it must have absorbed a certain amount of energy. And in the same way, that energy needs to have come from the spirit burner. So that's the concept. I think the best way to approach questions like this is to just go through an example. Okay, so I've just written an example here, which states the following. So 0.355 grams of methanol, or CH3OH, undergoes complete combustion in a spirit burner, which raises the temperature of 100 mils of water from 20.24 degrees Celsius to 37.65 degrees Celsius. And then the question is asking us to calculate the heat of combustion, or change in enthalpy, of methanol in kilojoules per mole. So this is a pretty standard question you will find, which asks this sort of format of questions in which you have to find, using specific heat capacity, how much energy is absorbed by the water, and then figuring out based on how much of the fuel we burn, what the generalized heat of combustion is for that compound. So the first thing I'm going to do, so step 1, is going to be finding how much energy, so finding the amount of energy in kilojoules, finding how much energy is absorbed. So this is going to be a pretty straightforward section. We're just going to use that Q equals mc delta T formula to find out how much energy the water has absorbed. So if we recall, Q equals mc delta T. So the mass of the water is going to be 100 grams. Now, the density of water is about 0.997 grams per mil. So it's very close to 1 gram per milliliter. In the exam, I'd probably recommend using this conversion factor, especially if you're going to a high number of significant figures. But for the sake of this example, I'm just going to say that 100 mils is equal to 100 grams. So it'll be 100 times 4.18, which is the specific heat capacity of water. And you multiply that by the change in temperature, which is 37.65, which will be the final temperature, or which was the final temperature, I should say, and the initial temperature, which is 20.24. So if you put that into your calculator, you get a value of 7,277 joules, or 7.277 kilojoules. So that's step 1 complete. Now we have to go to step 2. So if we scroll down here, step 2 is going to be finding how much of the fuel we have in moles, because the question asks us to give the answer in kilojoules per mole. So find number of moles. And again, this is pretty straightforward. So we're going to use the formula, which is also in your data book, which is the number of moles represented by the letter N is little m, or mass in grams, divided by the molar mass of the compound. So we have 0.355 grams divided by the molar mass of methanol, which is 32, and that gives us 0.0111 moles. So then our final step, which is step 3, is just to find the answer, which is the heat of combustion in kilojoules per mole. So we have the amount of energy that the water has absorbed, and for this question, we're just going to assume that all the energy released, so all the energy that was released by combusting the fuel, so all the energy released is equal to energy absorbed. So with that being the case, the answer would just be 7.277 divided by the number of moles we have. So this is the energy that was absorbed, consequently the energy that was released by the fuel, 0.0111, which then gives us an answer of 656 kilojoules per mole. And we will write this as a negative, because just to indicate that this energy is being released by the fuel, and because it's an exothermic reaction. Now, if we compare this to the actual combustion of fuel for methanol according to the data book, we'll see that this number is actually a bit lower than we would expect. I think methanol has roughly a combustion of fuel of around negative 725 kilojoules per mole. So that loss can be very easily explained by the fact that this statement usually isn't true. Usually there is some loss that occurs due to other aspects of the surroundings being heated, or not all of the energy being converted straight into heat. So in other questions and other examples, usually a conversion factor is applied. So from this original answer we get here, we might have to then divide this by like 0.9 to indicate that only 90% of the energy is completely absorbed, or other sorts of conversion factors like that. That really depends on the question. So for the sake of this, we're just assuming this statement holds true, but often cases that's not true. So that's just something to be mindful of. But other than that, this is kind of the basic format on how to answer these sorts of questions.